All right. Hi, everyone. My name is Sumit Sarbadhicary. I'm a CCAP postdoctoral fellow at The Ohio State University, United States. And I'm going to talk about where stars explode in the interstellar medium. And this is an exciting application of centimeter and millimeter wavelength maps that hopefully Eric Koch has already introduced. So one of the major goals of the Square Kilometer Array and the ngVLA is to understand how galaxies evolved, how structure formed in the universe. And one of the major tools that we have at our disposal for understanding this process is cosmological simulations. And these are just two examples that I'm pulling from the literature. This is Illustris and Fire. There's many more, but basically you throw in the physics of star formation, baryons, dark matter, gravity, magnetic fields, heating and cooling, and watch structure evolve from first principles. And we've achieved a surprising amount of realism in these simulations now, not only at the scales of cosmic web, but also at the scales of individual galaxies. But what we have learned in the last 20 years or so is that it is very difficult to reproduce quantitatively the landscape of galaxies without reproducing the small scale physics of star formation and stellar feedback. Basically, gas clouds are trying to turn into stars as a result of gravity and radiative cooling, and stars are applying pressure back on the gas in the form of stellar winds, supernova, and H2 regions. So this process is called stellar feedback. And without accurate feedback models, as I mentioned, it is very difficult to reproduce galaxies accurately. And here's an example of the same galaxy reproduced by Smith et al. 2018. This is one of many people who have simulated galaxies with different feedback models. Okay, and in each case, you get a different galaxy. On the top left, you have a no feedback case, so a galaxy without any feedback, and you can see that the galaxy does not look like a galaxy. All the gases turn into stars, nothing stopped that from happening. In the other cases, you have feedback, the galaxies look more realistic, but there's differences morphologically. And if you look at other metrics like star formation rates or gas densities or gas temperatures, there's going to be even more differences that can be noticed. So really one of the major priorities of the galaxy evolution field is to understand stellar feedback in more detail. So I'm going to talk about supernova feedback. How does that work? Suppose you have a supernova going off in the interstellar medium. In a few thousand or 10,000 years, the shock is going to superheat the gas to X-ray emitting temperatures and create a bubble of hot gas of a few hundred solar masses. This is called thermal feedback. This is the origin of hot gas in the universe. And then over time, the hot gas cools, but the swept up gas from the shock gains a significant boost in momentum, which eventually turns into gas motion, turbulence, outflows in the ISM. And through a combination of this thermal and momentum feedback, supernovae drive a number of major physical processes in galaxies, such as I mentioned, outflows, turbulence, hot gas, cosmic ray acceleration, dispersal of clouds, and the cycling of metals synthesized in stars. So it's really important to understand the physics of supernova feedback in detail. And one of the things that I'm going to focus on is the impact of the ambient ISM environment of supernovae. Suppose most of your supernovae explode in the low density gas in between clouds. The simulated ISM, and this is simulation by one group of the many groups that have done this kind of study. The simulated ISM looks like this. You have this thick, overpressurized disk full of embedded hot bubbles driven by correlated supernova, and you have cold, dense clouds that didn't really feel the impact of feedback because they mostly shaved out the outside, didn't really impact from the inside. On the other hand, if supernovae go off inside dense molecular clouds, the simulated ISM looks completely different. It's thinner, most of the molecular clouds have been shredded, and there's basically no hot gas because no supernova is going off in the low density gas. So this shows that ambient densities of supernovae are critical to how supernova regulate galaxies. They regulate the star formation rates, they regulate the outflow rates, they regulate the metal cycling, and so the ambient density in turn kind of affects our understanding of how supernovae drives the evolution of galaxies. This brings me back to my original slide, which is where do stars explode in the ISM? Because we have a scattered idea of what happens. We know that massive stars evolve in dense gas, but we also know that they move around in the disk. We know that they blow powerful winds, which can affect the gas. So what is happening? What's a coherent picture of massive stars and their gas environment? And this is something I'm trying to understand from observations. And until the JVLA and ALMA came, this was really difficult to do. It was really difficult to understand the cloud scale environments of stars and supernovae. So I'm showing two surveys that I'm actively involved in with this philosophy. On the left is the local group L-band survey, which again, I'm hoping Eric already introduced, but this is a detailed survey of atomic hydrogen and radio continuum in our local group. And on the right is the FANG survey of molecular gas. And now we have JWST, HST, and many other telescope. It's the most detailed multi-wavelength album of galaxies in the universe. And this is just showing how far we have come as a result of ALMA. Before ALMA, most of our molecular gas information was on the scale of kiloparsecs. And with ALMA, we have sub-kiloparsec down to 100 parsec, 50 parsec scale information of individual molecular clouds across the entire star-forming disk of galaxies. So this is perfect for studying the environments of supernova. So with a PhD student, Nesmaker Chen at Ohio State, we looked at the dense gas environments of nearby supernovae. And I believe this is the first time that we've looked at the individual molecular cloud scale environments of supernova. We looked at 63 of them in 31 galaxies. And I encourage you to look at the paper for details, but one of the major and interesting findings of the paper is that 60% of type 2 supernovae or core collapse supernovae are not coincident with dense molecular clouds, which means they're injecting energy into the diffuse gas and not the dense gas. Maybe the 40% is exploding in dense gas, but the 60% in diffuse gas. So we're pushing ahead on this. We're looking at dust, we're looking at ionized gas in the environment. But one of the frustrating limitations is that, number one, supernovae are rare. Within 20 megaparsec, it is very difficult to have thousands of supernovae. It's just the rate is too low. The second limitation is that we don't have detailed atomic gas information at the scale of molecular clouds like we have from ALMA. And that makes it a bit complicated because atomic gas is a major part of the ISM. It is a significant fraction of mass and the pressure in the midplane. And it accounts for the total density of the gas that the supernova is evolving in. So unfortunately, that restricts me to the local group, which is something I've been pursuing with a student at Ohio State, i.e. to look at the supernova environments in the local group galaxies. The advantage is that, number one, you don't have supernova, but there's a lot of massive stars, specifically evolved massive stars like red supergiants and Wolf-Rayet stars, which we know are going to explode in the future as supernova. We know that red supergiants explode as type 2 supernovae, and we know Wolf-Rayets plausibly are connected to stripped envelope supernovae and long gamma ray bursts and black holes. We also have cloud scale or subcloud scale observations of CO and atomic ISM in these galaxies. It's really the only place where we have cloud scale atomic gas and kinematic information. And this is a survey led by Eric Koch right now. I'm just showing our survey footprint. And if you combine these two together, you get this detailed map of individual stars that will explode as future supernovae and the individual molecular cloud environments around these supernova. So with this information, we can convert the line fluxes into a density, and if we assume a scale height, we can get a volume density. Put that together, and that's what the density distribution of these stars look like. So before I elaborate on this, what I want to highlight is that this is a new way to actually validate models of feedback in cosmological simulations. The density distribution is something that simulations are increasingly able to capture now because they are able to resolve down to smaller baryonic masses. So on the left is a cosmological simulation of a dwarf galaxy at the scales of individual stars. And you can see that they are able to observe what the density at the location of the supernovae are in their simulations. And on the right is a lower mass, lower resolution, larger volume simulation from Eagle, where they can also get this information because they're kind of critically thinking about how to distribute the supernova energy. In both cases, the point is they can look at the density of the supernova going off in the star particle, and that can be compared with our observations. This is a completely new way of actually checking the nuts and bolts of simulations directly from observations. And this is something that really came up at the ngVLA meeting last year in New York, where we were trying to increase the amount of crosstalk between observers and theorists in galaxy field. And I think this is a step in that direction. What we also learn from this is that the total density is kind of correlated with progenitor mass. So Wolf-Rayets are 30 solar mass stars or higher. Red supergiants are between 8 and 30 solar masses. And the limited sample size only let me divide this into 3 age bins, or 4 age bins. But you can see that there is an increasing trend. And this just shows that younger stars are more likely to evolve in dense gas and more likely to explode in dense gas. However, if you look at the molecular gas at the locations of these supernovae, things start to get a bit interesting. This is just showing the surface density of molecular hydrogen at the location. And what we find is that 70% of red supergiants do not have any detectable molecular gas at the pixel location. This is kind of consistent with what NESS is finding with the type 2 supernova. No surprise there. What's interesting is that the Wolf-Rayet stars, 40%, more than 40% of the Wolf-Rayet stars, and these are the most massive stars in the galaxy, they also don't have any detectable hydrogen at the location. Just to give you a picture of this, here's a little patch of M33 where you can look at the stars. The molecular clouds are in green contours, and I circled the Wolf-Rayet stars with yellow circles. And you can see that indeed they are kind of separated. They're not inside the contours of the molecular clouds. Many of them are kind of loosely associated with OB associations, so they're not really running away at a very fast velocity. So the only thing that can explain this is the gas that these Wolf-Rayets had around them has been cleared up, maybe by pre-supernova feedback, maybe by prior supernova episodes. But that shows the importance of actually including pre-supernova, prior supernova feedback in galaxy evolution models. And it gets even more interesting when you look at higher resolution data. So I just said 40% of Wolf-Rayet stars have no detectable H2, which means the rest of the 60% have detectable H2. Maybe they're exploding in molecular clouds, right? Well, here is a little patch of M33 where we have a Wolf-Rayet star very near a molecular cloud. It's basically in the low resolution data, it looks like it is evolving on the edge of the molecular cloud. And if it explodes, it's just going to slam into the cloud itself. When you look at higher resolution data, and we have this from the archive, it looks very different. There's actually a cavity surrounding the Wolf-Rayet star. And the molecular cloud itself is very complicated. It's actually a colliding cloud system. This was looked at by Hitatoshi Sano in detail. But this cavity means that the Wolf-Rayet, if it explodes in the future, it's going to explode in this low density gas where it's going to retain its thermal energy over the size of the cavity, which is about 20 parsecs. If it exploded in dense gas, if it exploded in the molecular cloud, it would have lost all of its energy within 6 to 12 parsecs. But here, it's actually going to be able to impact a much larger spatial extent as a result of this cavity. And if you do the math, you can kind of show that this cavity was probably produced by a supernova. It could have been produced by the O-star winds of the Wolf-Rayet itself, but that's not as important as the fact that at high resolution, there's a lot of details that we can infer across the environments of these stars. So it's really important to kind of pursue this. And on that note, there's a lot more I can talk about, but this whole symbiosis of stars and supernova and their gas environments, I think, has a very exciting future. With ngVLA and SKO, we are basically going to be able to do whatever we do in the local group all the way out to maybe 10 or 20 megaparsec, which is a significant increase in volume, the number of galaxies, and the number of stars that we can actually observe. And then these telescopes are going to have lots of friends. There's JWST, Roman, Rubin, which are going to give us some of the best astrometric and photometric observations of stars and supernova that we have so far. So we can really kind of marry these two fields together and look at the detailed observational picture of where stars and gas are coexisting. So on that note, I'm going to end my talk. So where do stars explode in the ISM? Well, younger massive stars are exploding near denser molecular gas, but a significant fraction, between 40 to 70%, are actually exploding in the low density ISM. And this is most likely a result of pre and past supernova explosions. And what's exciting is that these measured densities can directly constrain subgrid models of cosmological simulations. And this is, I think, a new direction that we should be quite excited about. And with the ngVLA and SKA, we're going to be able to probe parsec scale, subparsec scale substructure in these galaxies well beyond the local group. So that is something to keep an eye out for. Thank you so much, and I'm happy to take questions.
Thanks very much for that great talk. We have lots of time for questions, so.
Hi, thanks for the really nice talk. Very interesting, also the connection to simulations. But my question is about the observations. So do you worry at all about projection effects and the fact that these fractions may be upper limits if you're linking in the dense gas and the star in projection?
Yeah, so the projection definitely is an issue, but we are and we are thinking of ways to compare it with simulations, because simulations do have the 3D information, but they can also average over their 3D along a given line of sight and inclination, and that's something that we can also compare with. And some of the preliminary simulations that we're looking at, they do have quite a significant fraction that's exploding in low density gas. It's just a bit of cosmetics that we have to do from that side.
Yeah, awesome stuff, Sumit. That was really awesome talk. But it's outside my area of expertise, so sorry if this is a dumb question. But with Wolf-Rayet stars, right? They're obviously clearing their neighborhood. These powerful winds are often part of. They're often binaries, companions that have interacting shocks going on. But they're also producing a ton of dust, right? Which you're not sensitive to. There's a lot of dust production going on. How does that impact the following supernova, or is that just not enough dust for the type of environment? Because you're very sensitive, obviously, to the gas environment, but I was just more interested in terms of dust and its influence on the supernova.
Yeah. So are you asking like if we're missing Wolf-Rayets because of dust, or?
Yeah, and also how does that impact the following supernova, right? So you're saying you're clearing out this neighborhood, right? And you get a different type of supernova in, say, the molecular cloud, but these things are still surrounded by a ton of dust, and that can impact how the supernova evolves as well.
Yeah, so I think, so in terms of impacting the supernova, so I don't think people have actually looked at this in detail, but you need a lot of gas mass for the shock to actually lose all of its energy to that, dust or gas that is hovering around. So most of the supernovae that explode, even if they are ejecting a lot of gas before the supernova, they're not going to lose much at that circumstellar material. Most of it is going to impact. Most of the momentum is going to go into the ISM still. Okay. In terms of missing Wolf-Rayets, there's not going to be that many, maybe a few. I looked at the star formation histories, and the Wolf-Rayet catalogs are pretty complete.
Okay, thanks.
Other questions? Is there anything online? No? Oh, yeah.
Yeah, thanks. Neat talk, and particularly that high resolution molecular with the Wolf-Rayet in it. Any thoughts about implications for escape fraction of ionizing radiation from galaxies?
Yeah, so there are people in the collaboration that's thinking about this with ionized gas. it's not something I can directly constrain from these from this data set that I'm looking at. This is mainly just looking at, the motion in the gas. But there are IFU surveys where we can constrain the amount of diffuse ionized gas, which is basically produced by the escaping radiation. So yes, that can be constrained, but not from this data set directly.
So marrying that question with the beautiful images that are coming out of JWST of disks of galaxies and what look like lots of bubbles and the like, are you maybe reinforcing that idea that there really is the material being pushed around on fairly large scales because of winds and or supernovae or whatever, but that you're not losing a lot of your energetics inside the molecular cloud when things go funny?
Yeah, that is kind of what I think I'm heading towards. But what I'm also trying to say is that, this is not going to be the case for every star. It's only going to be the case for like the highest mass stars. Okay, a lot of the red supergiants are still consistent with, interacting with atomic gas, and those are, still going to be imparting energy, probably producing turbulence. So there's a bit of a dichotomy there that I'm pushing at.
Okay, let's thank our speaker again. And